Does it work? So I guess part of the reason for this workshop is to study the interaction between number theory and mirror symmetry. So I will try to say a few words from arithmetic point of view, motivated by Canara's question, which he discussed in his lecture yesterday. So what I want to ask is the slope mirror symmetry is initially I was actually planning to study this problem as a related one as a student project, but turns out it seems to be a little bit more complicated than the student project. So I will start with this example studied by Candaras and other people, this quintic family. This projective, in projective space, I look it over a finite field, so this is most projective one. Actually, I want to correct one error in my lecture yesterday. So in my lecture yesterday, I gave this example, and of course, this is a condition for f to be delta regular. Then I remove the case where p dividing m plus 1. So if p dividing m plus 1, it is actually better, because then it's always delta regular if lambda is not 0. So we don't have to throw away p dividing m plus 1. Therefore, in the statement theorem, we should just remove that condition, drop this p dividing m plus 1. So it is actually for better, becomes better. Therefore, it's for all p. So similarly, I don't need to remove p is 5. And then there is this mirror, which is also smooth projective, but not hypersurface anymore. And then you have two zeta functions. So one is the zeta function, so all of them smooth projective. So the zeta function of the quintic is, of course, of this form. It's hypersurface. And then numerator given by p lambda t. And numerator will be a polynomial with initial coefficients of degree 204, and is a pure weight 3. Now similarly, the zeta function of the mirror one has a somewhat different form. And it's numerated by p w lambda t. And here again, this is a polynomial with initial coefficients of degree 4. So Candaras was trying to find some symmetry between these two zeta functions. So the first one he was looking for whether one is the reciprocal of the other, because the degree changes if you just switch numerator and denominator. That, of course, is too strong, because then and it cannot hold. So then we try to look some weaker version of whether that holds or not. So the weakest version is if you just change the degree, if the degree will interchange when you replace numerator by denominator under this mirror symmetry. So, what is the, okay. What is the Hodge polygon in both cases? So, let's say the Hodge polygon, let me denote this by, comes from, let's say, suppose this comes from delta, this comes from delta star. So the Hodge polygon of delta will be just, will be the Hodge polygon of the numerator, which is, okay, what do we have? We have 1, 2, 3, 4 sides, and the slope 0, 1, 2, 3. And then the length will be, horizontal length will be, this will be 1, 101, 101, 1. So the Hodge polygon, let's see, the Hodge polygon of this quintic is this one, which is just equal to the Hodge polygon of the denominator of the second one. So the Hodge polygon of this one is exactly 1, 101, 101, 1. Slope 0, 1, 2, 3. Slope 0, 1, 2, 3. So this is like the Hodge polygon of the denominator of its mirror. Of course, this is just the Hodge symmetry, so that's nothing new. And of course, similarly, right? So similar Hodge polygon of the delta star, which is just Hodge polygon of the mirror manifold, which is just this one. 0, 1, 2, 3. But now the length becomes 1, 1, 1, 1. And this one is just the Hodge polygon of the denominator of the number of this is the zeta function. This mirror will be m lambda. So basically the Hodge polygon and the Hodge polygon of its mirror switch under the mirror map. Okay, so that is classically long, it's just Hodge symmetry. So we want something finer than this one. We try to look for something more symmetry, which is arithmetic in nature. And then there are two types of question aspect you can look at. One is look at the discrete symmetry, and another is kind of continuous symmetry. Of course, zeta function contains both. Just as I said yesterday, a root has two parts. One is its size, the other is its angle. So the absolute value, which is the size, that gives you the discrete invariant. The angle gives you the continuous invariant. Therefore, we should break this into two parts. One is the discrete part, one is the continuous part. And I'll just say a few words about the discrete part. And for the discrete part, then you take the absolute value because these are pure. And for the complex absolute value doesn't tell you anything new, so we try to look at it from periodic point of view, the slope. So Newton, the Hodge-Parkin switch and the mirror, we know the Newton-Parkin is something that is finer than Hodge-Parkin, so we can ask whether the Newton-Parkin switch or not. So question. Newton-Parkin of this mirror one of them is M. Under the mirror up. Well, if that is switched, that would be striking. Because then one of them is trivial, the other one is non-trivial, so if that is true, then you get a lot of things for free. So if that is true, so if the Newton-Parkin, okay, actually, what Newton-Parkin we're looking at? This is not good. So we're trying to, we want to switch the numerator and denominator, the Newton-Parkin numerator and denominator. So this question is not process, actually the Newton-Parkin of numerator, here, Newton-Parkin of numerator of zeta function of lambda t. If you switch, does it go to the Newton-Parkin of denominator of the mirror? Okay. So if you look at this one, so the Newton-Parkin of this m lambda is something unknown, which we would like to study. The Newton-Parkin of the denominator of the other one is trivial, is given by the Hodge number. So if this mirror holds, if these two switch, that means the Newton-Parkin of this one will be given by the Newton-Parkin of this one. And this one is independent of p. That means the Newton-Parkin of that will be constant. Not just constant, actually equal to the lower bound of the Hodge-Parkin. Because this one, the Newton-Parkin of this one is just the Hodge-Parkin of that one. So if the Newton-Parkin actually is switch between numerator and denominator under the mirror map, then basically you know all the slope. So that is obviously cannot be true. Even that is the truest one. Because we know the Newton-Parkin is not constant. The Newton-Parkin still depends on the parameter, but in a milder way than the angle. So this cannot be true. Therefore, so it still depends on the parameter. So if Newton-Parkin is not true, then we can ask even weaker question. What about the generic Newton-Parkin? Next. Okay. So let's say generic slope symmetry. So if you look at this basically we want the relation between the Newton polygon of the numerator of the first manifold and the Newton polygon of the denominator of the second one. So now we can ask whether the generic Newton polygon of this one equal to the Newton polygon of the denominator there, which translates into this question. If it holds, basically this would imply the generic Newton polygon of this one parameter family of polynomial is equal to the Newton polygon of the denominator of the mirror manifold, which is this one. Which is, of course, just Hypersurfaces of the manifold itself. And if switch similarly generic Newton polygon of the mirror manifold, whether equal to the Newton polygon of the denominator of this mirror, which would be 1 minus qt, which is just Hypersurfaces of W. So that would be what is the generic slope symmetry if it holds. Now, of course, yesterday I defined the generic Newton polygon, but there I studied the universal family, the big family. Here it's a much smaller family, it's a one parameter family. So even if you know the generic Newton polygon of the big universal family, it does not mean you know the generic Newton polygon of a smaller family, because Grothendieck theorem's specialization theorem says when you specialize the parameter, the Newton polygon will go up. So this one will lies above the universal generic Newton polygon, which I defined yesterday. Of course, if you further specialize this parameter to one value, then we know it's force. Okay. So that is, from a slope point of view, that is the best you can hope. Okay, so once we have a, okay, this one is just, okay. Once we propose this question, then we can look at it, so what can be proved. And it turns out, using the result I discussed yesterday, we can, one half of that is already true, in fact. So part 2, second part is true. Is already true, in fact, for all p, not just for one p. This is because of what? This is because the second one, this is because the delta star is a funnel. Because the second one is funnel, so if it's funnel, then this one parameter family is actually ordinary for all p, as long as your primary base is non-empty. So that's already true. But the first one, it's not clear that it is true. First one, because your delta is big, you only consider one parameter family. So the universal generic Newton polygon doesn't tell you much about this one. We all know this one lies on or above the universal generic Newton polygon. But if you use the star decomposition described yesterday, so you can show the first part is true if for all the prime p is congruent to 1 modulo phi. So that gives you a partial result on this. It is possible this is true for all p, but so I'll leave that as an interesting problem to study. So question is it true for all p? So question. And if that is true, then that means for this example, this one parameter of conic variety, then you would have this generic slope symmetry. Okay, anyway, so that's a little bit of the arithmetic mirror symmetry to get started. Then I believe there will be a continuous symmetry from periodic point of view, the angle, the unit root part. So, okay. It turns out I still have some time, so maybe in my lecture notes on the web I have chapter 3. So now I want to quickly go over chapter 3, which is the periodic variation. That is basically discuss the continuous part. So far I've been restricting to the discrete part, the value, the slope, and next we need to look at the continuous part. So periodic formula for zeta function. So let's say we look at a polynomial, long polynomial, that's a regular polynomial over a finite field. So Q is P to the 8th power. Now we're going to study the variation of this zeta function. So when lambda vary, how this total zeta function vary, not just looking at the slope. So previously we were just looking at how the slope, how the weights vary as the parameter vary. Now we're looking at the horizon. We're not going to throw out anything, just the horizon. Then of course we know then the zeta function is the product of some trivial factor times the non-trivial part. So we need to understand the non-trivial part, how it varies. And here, the non-trivial part is a polynomial with integer coefficient of degree d of delta minus 1. Okay? And of course, suppose this is a determinant of some four-base map. This point acts on the cohomology space. So, since now we're not going to throw away anything, then basically we want to find how this map varies. How this map depends on lambda bar. And ideally we want to have a formula to write on this map, or write on this matrix, in terms of lambda, hopefully as an analytic function of lambda. But lambda bar is in the characteristic P, and its value is going to be characteristic 0, so we cannot just simply use a power series or function of lambda bar. Because if your input, if you have power series, your variable takes value in characteristic P. When you sum, it's still in characteristic P. You're not going to get a characteristic 0. Therefore, we have to, in order to get a formula, we have to lift this lambda bar to characteristic 0, which is one of the lifting would be Teichmüller lifting. And once that is said, then we do have actually a formula. This is just the sort of a metric the interpretation of the notion for Neff crystal. So we know this cohomology, relative cohomology is locally free. That means there is locally on the parameter space, we can write the matrix or the map as this is the formula. There is this analytic matrix such that lambda is Teichmüller lifting, lambda bar, and the A lambda will be a power series with particular integer coefficients. Actually, a matrix with a power series which is convergent on the closed unit disk. So when we put in this lambda will be roots of unity. We plug in lambda as roots of unity into this analytic function. It actually converges. So that gives you a periodic integer matrix. And because lambda could be an extension field, so you multiply all of its conjugate. and take Hurst polynomial, that will then have a periodic integral coefficients. So that's a formula. This formula tells you how it varied analytically. Because basically this tells you when lambda varies, you actually have an analytical matrix, analytic function. You plug in lambda, compute the variables, and that gives the matrix. The matrix is varied. And in fact, this has this Hodge filtration, this block form. Okay, so A lambda is a periodic analytic matrix over, say, ZP. Analytic where? Analytic, in fact, one can show the overconvergent. Analytic in a disk bigger than the unit disk. So when you plug in roots of unity, it does converge. Of course, it's not going to be analytic everywhere, but it's analytic in the region where you're interested in. And furthermore, of course, we know that zeta function related to the pure-phase differential equations, so this map must be related to differential equation as well. And that is also contained in the notion definition of F crystal, which in terms of matrix language, I assume P is bigger than 2, then one can show, one can actually take, of course the choice of matrix is not unique, so one can actually take the matrix to be of this form. Say C lambda and C lambda P to the inverse matrix, whereby let's just change the coordinates so that 0 is actually a regular point. And lambda, C of lambda will be just the fundamental solution matrix. Solution matrix of this P-half equation. So this is the general phenomenon. It's always true in such a situation. Now, I do not know how to prove this, if this is true for P is 2 or not. So in the literature, usually people don't say that. That could be true, but the proof which I know only works for P is bigger than 2. And in fact, the differential equation, if I started initially, is not the P-half equation. It's actually a differential equation with analytic coefficients. However, if it tensor, because I work with over Zp, so everything is integral. If I tensor with Q, then I can actually change my differential equation isomorphic to the P-half equation. That I can be done. I can do it if P is bigger than 2. However, for P is 2, I don't know how to do that, but I can replace an analytic differential equation by an algebraic one, which is still different from the P-half equation if in the case P is 2. So anyway, there is some subtlety there, which is I have not understood completely myself in the case P is 2. So basically, to use the P-half equation, you need to use a simpler splitting function. Instead of use this exponential times this infinite big power series, you just use exponential pi t. That one will give you exactly the P-half equation. If you use the big one, that will give you the differential equation. The coefficient of differential equation will not be rational function. Will be just the power series. Will be an analytic function instead. So this theorem, this is just translation of the notion of F crystal in concrete language. So that's the variation, the variation of total zeta function, sort of this variation of total coordinate space. Then we know the slope distinguishes the roots. So that suggests your total coordinate space can actually decompose into smaller pieces in some sense, because we know the eigenvalue to decompose. That is in fact true. That is the so-called Hodge-Newton decomposition. That means the F crystal actually has a filtration into sub-F crystal. So next we look at this periodic formula for unit roots. So the previous section basically tells you the formula, analytic formula for the whole Zeta function. Right now, suppose we know that exactly one unit, periodic unit, or that let's say exactly 5 units. They want to have a formula just for 5 roots. We want to have a formula for just for those roots with a fixed slope. And of course, so the first part of the question, you have to know exactly how many roots with a given slope. If you do not know how many roots with a given slope, then you don't know what kind of formula, what shape the formula should take. If you know there is, let's say, 5 roots, exactly 5 roots everywhere, which are units, then that means these 5 roots are specified. You know there are 5 roots. So you should look for a 5 by 5 matrix, which will give you the 5 roots. And if sometimes there are 5 roots, sometimes there are 4 roots, then of course, then you don't know whether you should take a 5 by 5 matrix or 4 by 4 matrix. So anyway, so that's why we need to understand how many roots with a given slope. And that was exactly the slope discussion at yesterday. So let's look at the case, nice case where let's assume P is ordinary. In this case, okay, ordinary, therefore we let HP of delta be the subspace of those delta regular polynomial such that F is not just regular but ordinary at P. Ordinary. So that means you shrink your space, parameter space, a little bit more so that on this subspace, everywhere it is ordinary. Therefore, in fact, because it's ordinary, this turns out to be a Zariski open dense. Open dense. So in general, that would be just open. But open could be empty. But since we assume it's ordinary, general ordinary, so it's not empty, so it's dense. So we just now we look at those random polynomial which is ordinary. Then of course in this case we know this polynomial, the non-trivial part of the zeta function has exactly h delta k plus 1 reciprocal roots with slope k. So for each k, you know exactly the number of roots with a given slope. That means we know, for instance, for given k, we know there are this many roots with that slope. So we can ask whether we can find a formula, analytic formula, for just precisely for these hk plus 1 roots. Of course, so fiber by fiber, then you can certainly factor this polynomial arithmetically. So this is a polynomial with integer coefficients. And you know it's Newton polygon, which has exactly this many 0, reciprocal 0 with slope k. So therefore, you can factor in terms of slope, what it does pk, say, I use pk lambda bar t, k from 0 to minus 1. Now, this is a polynomial with integer coefficients. When you factor into a pure slope part, the roots will be in an extension field. So you cannot expect that we have integer coefficients anymore. They have, in general, they're just algebraic number because you just take a partial product of the roots. However, we viewed it periodically, then the coefficient is actually in Zp. So it is integral over Zp, it's rational over Zp. So it intersects with, so we know it's algebraic number, but it's also, because roots will not be in Zp, but the product will be in Zp. So that's actually a polynomial. So each one is actually a polynomial in there, and it's pure. Each pk will have a pure slope exactly k. Right. So then, therefore, the previous result tells us we have a periodic analytic formula for the whole zeta function. Now we ask whether we can get a similar formula for each factor or not. So this sort of a little bit slightly deeper to just go one step further. From F crystal point of view, that means you're asking whether your F crystal is reducible or not. Can be written as has a filtration as an F crystal. And that is in fact the case. That means basically, here of course, we factor this polynomial only fiber by fiber. And that theorem tells you can simultaneously factor it analytically as lambda vary. Here, of course, for each given polynomial, we can factor it this way. But as lambda vary, then we don't know whether we can simultaneously factor it or not. This Hart-Newton decomposition basically tells you can do that. You can simultaneously factor it. So then the question, what is the formula for this one? The pure slope part. And the result is exactly the same, similarly. So again, Zariski locally, you can write this pk about t is a determinant of some matrix which depending on k. And here would be, because we know the slope is k, so that means we can pull out q to the k, a factor there, t. And where this will be, then, so will be slope 0, that means that will be invertible. It will be unit, that will give an invertible one. And where Frobenius, you can write it similarly as an analytic matrix times its conjugate. Lambda bar is in F pure A, and lambda is Teshmiller-Lifton. So of course this one we have rank. This is the matrix we have rank GL H k plus 1 times H k plus 1. So it will be a unit, invertible matrix in the range of analytic function on this ordinary parameter space. And similarly, this submatrix, the smaller matrix, is also related to the differential equation. Of course, then you don't need to use all the solution. You only need to use a part of the solution. And that is, which solution involved, that depends on, I think, the nature of the singularity of the differential equation. Okay, so that's just the meaning of analytic variation for the zeta function as well as the unit root parts. And this gives you the information about how the continuous part of the roots vary with parameter. Basically, in some sense, they vary in an analytical way, periodic analytical way. And these functions, really analytic functions, they're not algebraic functions. So that's a connection with differential equations. And in some cases, actually, you can find explicit formula for this in terms of solution of differential equation. I think Toric computed some example in the case of elliptic curve, case-free surfaces. You actually give explicit formula in terms of this hypergeometric differential equation in certain cases. So I still have a little time. And then now we can start to discuss a little bit more from an arithmetic point of view, from number theoretic point of view. So once we have this formula, analytic formula, which tell us more or less how the roots and the zeta function vary, then we try to understand from an arithmetic point of view how these roots vary. Let's turn to another page. The periodic representation and unit root L function. So again, I will assume delta is ordinary. So we do know there is precisely how many roots with a given slope, and then we have this matrix AK lambda, which is gives a portion of the zeta function with slope k. So basically, you need to understand this one. Of course, that's one point of view, just to understand this map as an analytic function or from and its relation with differential equation. You can also try to study from Galois representation point of view, and this gives you a Galois representation. This is the Frobenius matrix of a periodic Galois representation of the parameter space, ordinary parameter space over Fp. That's a variety over Fp, so it has a arithmetic fundamental group, which is just the Galois group of the function field modulo the inertia group at those points. And that we can extract a periodic representation of rank hk plus 1 to Zp. And for each k, we have this. And how do we describe this Galois representation? This is a periodic continuous Galois representation. Well, we know the Frobenius elements are dense here, so we only need to describe the image at the Frobenius element. It turns out at the Frobenius element, at a given point here, lambda bar, this is exactly just equal to Fk lambda bar, which is just the product of this conjugate. And here, lambda bar viewed as a point in period A. In fact, the previous matrix description I gave, that was just like give you a so-called unit root F crystal. A unit root F, the category of a unit root F crystal is equivalent to the category of a periodic Galois representation. Now the total zeta function is not given by this polynomial. The total zeta function is not given by the curse polynomial of some periodic Galois representation at a Frobenius element. That's not true. Because periodic Galois representation, the eigenvalue always give you periodic unit. On the other hand, we know the zeta function has roots which are not unit, so you cannot expect periodic representation give you the zeta function. You can only expect periodic representation give you the unit roots. In fact, each unit root piece does give you a periodic Galois representation. And this Galois representation, of course, the transcendentals they're not compatible with the analytic representation, because rank is much smaller. The rank is just Hodge number. The analytic representation is a beta number. So you can think of the analytic representation is sort of irreducible already. And here, if you look at the periodic analog, it actually is reducible, decomposed into smaller pieces. So the sum of this Hodge number gives a beta number. So once you have this continuous Galois representation, then you can, in number theory, then you associate with their L function. Just take the Euler product of all closed points have the Curse polynomial of the scalar representation at the Frobenius lambda bar to the degree of lambda bar. And this is the power series. Where are the coefficients? Where would be the coefficients? So we know if you take the total zeta function, there will have integer coefficients. This is sort of the part comes from pure slope k part. So really comes from sum of the roots. Therefore, will be an extension field. Now, of course, if you work with Q bar, then certainly Q bar, okay. But when you work with Q bar, that's not really well defined because when you take the roots, these roots could be all conjugate, and it's not clear which roots has the given slope. So really, we view it from periodic point of view. There's a periodic integer intersected with Q bar, of course. So that's where the coefficients sit in there. It's not an integer anymore, but it's a periodic integer, and it's algebraic coefficients. So this is a so-called unitary zeta function, and which is Daqing defined, and he conjectured this zeta function as good as possible. Of course, ideally, remember when he proved the rationality of the zeta function, the key step was the meromorphic continuation of this L function, where he, and there, of course, because the coefficients of the L function are integer, so by this, and also it has a positive relative convergence of the complex number, so it forces it to be rational. And here, your coefficients, okay, they are periodic integer, but not integer. In fact, it's not in it. Let's say in Q bar, in fact, in general, you cannot find a single number field containing all the coefficients. So the coefficients are really, although algebraic, could be in a bigger and bigger extension field. And also, the coefficients are really in periodic number. So even if you prove it's meromorphic, that will not give you a rational function. It does not imply it's rational function. In fact, it's not. You know. So if it's not a rational function, and on the other hand, you want to hope it is a good function, what is the next class beyond the rational function, which is also nice analytically? So that would be a meromorphic function. So that is basically Daqing's conjecture, which is what has been proved. This is actually indeed periodic meromorphic in T. Meromorphic everywhere for each k. So periodic meromorphic means what? It means it's just like a rational function. You can write it as a quotient of entire function. For periodic entire function, you can write it as just product of linear factor over. So this is just generalization of rational function. Now you have infinite minus 0 and infinite minus pole. And this alpha I, beta j will be going to 0 periodically. Of course, over the complex numbers, this may not converge because you may need an exponential factor. Now, in periodic situation, the exponential factor is not entire, so that cannot occur. Has to be thrown away. And what's left turns out is already nice. Okay? So that's the meaning of the meromorphic continuation. So basically that tells you the units actually behave very regularly from arithmetic point of view. And once you establish the meromorphic continuation, then you can ask, what can you say about its observability of the zero, the location of zero in the pool? Just as we did for the zeta function, where we studied the complex observability, periodic observability. But here our function is roots of the real periodic number. We cannot ask for the complex observability. However, we can ask the periodic observability, which is what is the slope of this alpha I, and what is the slope of this beta j. Do we have a lower bound, like a Hodge polygon here? That's unknown. So there are many interesting questions, and I leave it to the audience to think about some of them.